Yeah, I don't know if there's an alarm today, but it's already past 6, so let's start. I would like to start a little bit with some motivation. Why do we care about surfaces in the first place and like objects defined on a surface? Like if you look at all what we discussed so far, it was usually, it gets way easier if you look into like an open subset of Rn, and it was everything like you had global coordinates, you had like x and y direction, and your life was pretty easy. So I would like to motivate a little bit, why should we care about like something that is like really happening on, say, like a sphere or something? Like why do we care about like objects that are not like only defined locally in a chart, but like something global? And as an example, suppose that we have the sphere and we have some vector field on the sphere. So it's a bit like, you can imagine that there's like some arrows that are like attached, and so like that's not a vector field on the sphere, right? Because like the arrows are pointing outside of the sphere. So it's not a vector field on the sphere, it's like a field of vectors in R3 that is defined on the sphere, but they are not tangent. So it's not a vector field on R2. And the question would be, like given that such a vector field, can you always kind of deform it so that it's nicely formed, and like you kind of like make them flat and like align them well so that they are tangent to the sphere. And I don't know about your morning program, but sometimes I have this one hair which just like I wake up and then like always like there's this one hair which just sticks out. And like here in that example, it's also what happens. So I let you think a little bit about, can you find like a vector on the sphere which is not vanishing at one point? So this continues. So like for example here, that would be a vector field which is non-vanishing, but then it has this non-singularity where it's not continuous, where it sticks out. Can you find like a vector field on the sphere that has like the property that it vanishes nowhere? Like on R2 it's very simple, right? I can just like point, for example, always in the x direction. That would be a vector field that is nowhere vanishing. Can I find something like that on the sphere? I'll let you think a little bit about that. So who thinks that there is a vector field on the sphere that vanishes nowhere? Just raise your hand if you think it's a 50-50 chance and like doesn't influence your mark. Just like raise your hands if you think that there is a vector field that vanishes nowhere. Who thinks that there is a vector field? Okay, so everyone else thinks like there is no vector field on the sphere that vanishes nowhere. Okay, so that's a pretty good intuition. No? Like if you think about it a little bit longer, for example, you might come up with a vector field like that. That would be the obvious candidate. You have a vector field that is like always pointing in the same direction. But if you look at that, then you actually have two poles where it just like doesn't want to be continuous or where it sticks out. And even if you try more complicated versions, you always find that like for some reason there is one point at least where it's non-vanishing or where it vanishes, or where it's like diverges to infinity, so where it's not continuous. So you can do that like play around and like come up with different vector fields, but all of them have this property. And that's actually a theorem which is called the Harry-Ball theorem, that like every vector field on the sphere has at least, if it's continuous or smooth, has at least one point where it vanishes. So that's it's really a like profound theorem, but also pretty hard. Like we can't, like it's too advanced for this course, but it gives you some idea that like things on the sphere already are like very different to the things that we can look at just like open subsets. And the sphere is a really simple surface, right? It's just like two open subsets glued together. So that's very astonishing that you can't find like a vector field that is nowhere vanishing. That has like some practical influences. For example, you can imagine like the weather forecast or the wind patterns on the Earth. They're really complicated, right? But you can continue think of that as a vector field on the sphere. So what this means, the Harry-Bohr theorem is implying is that there is always one point on the Earth where there's no wind. So I find it really remarkable if you think about that from like a concept. Like there's always one point on the Earth where you don't have any wind at that given instant. It's like a pretty cool result. And there are some applications also for very practical things. Like for example, if you engineer antenna, if you have like a point source, like say that it's like a radio antenna, and you look at like very far away from that, then you can think of that as essentially plane curves that are like arriving here. And if you remember your electromagnetism, then it's always you have a direction, and then you have two, the electromagnetic and the electric and the magnetic field are always perpendicular to the direction. So if you're far out, the direction is going in this way, and then the electromagnetic field goes upstairs or goes like to the right or to the left. So perpendicular to this direction outwards. So what that means is that the electromagnetic field is a vector field on a very huge sphere outside. So if you consider very far away from the point source, you have like a really huge sphere, and then the electromagnetic field is always perpendicular to the normal direction, so that means that it's tangent to the sphere. So that means like if you have a point source that sends out radio magnetic waves, then at some point, out very far away from the source, you always find a point where you don't have any signal. So like independently on like what kind of fancier design of your antenna you have like maybe something that sends them out like radio or like a little bit in a different way, it always means that like far away you have at least one point where you don't have reception. So that's also quite interesting and like something that you should keep in mind. So that's just like as an example that like these results that we have about global object on surfaces are really important. Also like has some applications. Today we still have a little bit of like foundations to and basic elements to clarify and to study. So today we talk about taking a derivative of a differential form. So last time we talked about when you have a function and you can take the derivative of a function on the surface. Today we will say like we have say a one form on the surface, and we would like to say how much does this one form changes from point to point. And then in the second part we talk about integration, which is always like coming as these two things coming always together. Like if you have differentiation, then you always talk about integration and vice versa. So that's the topic for today. And then next time we can like harvest the fruits, as you say, of that study and like really go back to what we're actually interested in, namely the geometry of surfaces. Okay. So I would like to start with what is called the exterior differential. I actually don't know where the word exterior comes from, but it's really just taking the differential of a one form. That's the content. So let's start with something simple, namely that suppose we have a function on a surface which is smooth. Then we discussed last time that df is a one form. One form, and that one form encodes how much f changes, and it not just like changes in one direction, but in all directions at the same time. If you're only interested in one direction, that's encoded if you evaluate it, let's say at some point in a given vector, and this is the change of f in v direction. we need one argument, namely this vector, to keep track of like in what direction we want to measure the change. So it's like, so that's why we have to put like one extra degree. So now suppose that alpha is a 1 form on S. So it already eats one vector as the information, but we would like to say how much alpha changes if you change at different points. So that's the information that we want to say. Like alpha is an element that lives on the surface, and we would like to compare, so to speak, the value of alpha at 2 different points and say like how much does it change. And then it's, because it's already eating one tangent vector, and we would like to keep track of the change in all directions, it makes sense that like the differential of alpha would be a 2 form, where we have like one additional slot, where we say like what kind of change in which direction we want to encode. Change of alpha in all directions. Would be a 2 form. So something that eats 2 vectors, and one vector you can think of is plugged into alpha, and then we get a function, and the other one is like taking like the change of that function. So that's like why we need like a 2 here. And that's very similar if you think about f as something as a 0 form. So the function is a 0 form, and then we get df as a 1 form. And similarly, what we now see is if you have a 1 form, then the alpha is actually a 2 form. Okay, but like of course we have to say what this d alpha means, right? That's like what we want to discuss in this lecture. So suppose for now that we accept that it would be a 2 form. So how would you define it? Of course we need to choose 2 vectors at the tangent space, the surface, and what we have to do is we have to define the value. So d alpha is like the exterior derivative, and if that's what we want to define, then we have to say what that value would be, right? So we have to say d alpha would be this 2 form. Maybe I write this here. Would be a 2 form d alpha. That we have to say like d alpha is really just like the name for the 2 form. So that's something that we need to say. Like we have to say for each point, plug in 2 vectors. What is the value? So you have to point like a value there. And what would be natural is that we have a alpha which eats one tangent vector, right? So what would be natural to just like plug one of these vectors in alpha and then change s of that function that we get. So that would be let's try that as an initial thing. So just as a warning, it will turn out to be wrong, and then we made it slightly less wrong, and it turns out to be still wrong, and then we fix that, and then we come up with the nice definition. But like for starters, natural guess would be to treat B1 as the direction of the change. this means is that we define a function on S by f of S equals to alpha inserted v2. So we have the vector v2 and we plug that into alpha at a given point. P. So that's we define that as a function. So we will talk about in a second if that's really a function or not. But like, let's keep it like for the idea is that like let's plug in v2 into alpha, and then we would like to treat that element that we get and change calculate its derivative in the v1 direction. So and then define d alpha as v1 v2 as the derivative in S direction of S in v1. Or if you want to write it a little bit more, like we can just insert the function, so that would be and we treat this one in the middle as a function. So that's a bit like symbolic. So, but there's a problem here, namely that this definition was supposed to be a two form, and a two form by definition is always antisymmetric. So if I change v1 and v2, I should get minus this v1, v2. So, but this one clearly looks like not symmetric, right? Here I plug in v2 in alpha, I get something, and then I take a derivative of that something in the v1 direction. Why would that be like the opposite of if I change 1 and v2? There's no reason why it would be antisymmetric. So let's try to fix that. So it's the problem number 1. Not antisymmetric. So the next guess, if it's not antisymmetric, then we force it to be antisymmetric. So we just take minus of the other side switched in the array. So the next guess would be d alpha of S1, V1, V2 equals to Ts alpha V2. And then we take the derivative in the V1 direction, minus, where we change the role. So that's now clearly antisymmetric. If I change v1 and v2, I get like exactly this term, and here it's a minus. So that's nice and antisymmetric. But there's one more problem in this kind of definition. You have like an idea what kind of mistake I did? So the problem that I did was like I defined a function on S, or I wanted to be. So I wanted to have like a function on S. But the problem is, in order to define the function on S, this one is a one form. So it eats tangent vectors and gives us a number, but it eats tangent vectors at P. And what I like at an arbitrary point. So in order to make the sense of this as a function, I would have to say what alpha of P for every P is. But I only have one tangent vector. Like I only have the tangent vector at one particular point. So the picture is like you only have one S here, and some vector v1 and say v2. But in order to define this as a function, I need to kind of extend v2 to get like a vector field so that I can say can say really that the alpha and V2 is like paired to give us a function. That's last time what we talked about. If you have a one form on the surface and a vector field, so a tangent vector at every point, then you get a proper function by this description. But not if you just fix it like one point. It doesn't make sense to say, for example, that you have a vector at this point, but you have certain planes here, which would be alpha at a different point. What it would make sense to plug in this vector in this one form. It doesn't make any sense to talk about it. They really have to be defined on the same point, otherwise the pairing doesn't make sense. So what this means is, if you, in order to make sense of this function, we would need to extend the vector to a vector field. But then the question is, and that's actually a hard question, is in which sense does this expression then depend on the extension of the vectors? So if I extend the vector v2 here to some vector field that varies, then of course even if alpha would be constant, then I would have like a non-constant function here. So then I measure take the derivative, then I measure the non-constantness, but the non-constantness is coming from the vector field itself, from the extension that I choose, instead of really coming from alpha. So that's not something that I would like to measure. So the idea is to choose a particular extension of the vector fields that are given by charts, instead of considering like some arbitrary extensions of these vector fields, or to these vectors to the vector fields. So maybe I'll write it quickly down and then give you the definition. We only have one tangent vector at the point S. No. Every point. Okay. So the idea is to not use arbitrary vectors, but like the particular ones that are coming from charts. So the definition of the exterior derivative is the following. If alpha is a one form, on the surface S, then exterior differential is the two form on S defined by the following. What we do is we define not an arbitrary vectors, but we take like a chart, and then we have certain vector fields we talked about, and the vector fields that go in x direction and in y direction, but not as in the x and y direction on the plane, but like really as vector fields on the curved surface. So these ones give us particular vector fields for every point, and then we plug in these two vector fields. And then what we do is we use this prescription over there to say that this one is Ts of alpha. Then we plug in the first vector field. So that gives us a function. So that's now a proper function, at least in some neighborhood where the chart is defined. And then we take the derivative of that function in the x direction. And then we subtract the same expression with the words from the opposite direction. That holds for every chart. Around the given point. So really, like what you should read this formula is that we have alpha, that's a one form. What we do is we take phi, which is a map is a map in our curved surface. That's there. There's a given S there. Here we have our nice directions, which are dx and dy. What we do is we kind of send it forwards to get some vector field on the surface. That would be the vector field phi in x direction. That's a vector field on at least the chart area on S. Now we have alpha, which is a one form on S, so we can plug in this vector field in an alpha at every point on this area to get some function, which is at least a function that is defined in this neighborhood. And then we have a function, and then we take the derivative of that function in the direction that is given by the y. So y would be like another vector field. And that gives us a function, this expression here. And then we take the derivative in this upper direction. And then we change the roles and plug in first the red vector field in alpha to get a function, and then take the derivative in the upper direction. So that's how you should read this formula. It's really like plugging it in to get a function, and then take the derivative of that function in this direction. So a few remarks about this definition. So first of all, the first remark is that it's really enough to specify this value here. That we only define d alpha so far as what happens if you plug in x and what happens if you plug in y as these vector fields. But in general, you have like two other vectors. But every vector, we know, is like a linear combination of these two vectors. So that's the first remark. because these ones are bases, so we can always write a detention vector as a unique linear combination of both of these vectors. So if you have now one vector that you plug in, then you can always expand this expression using bilinearity to reduce it to the case where we have x and y there. And then because it's antisymmetric, I also don't have to tell you what if there's y and there's x, how they are defined. So that's like the first one, that it's really enough to just say what alpha or d alpha is by specifying its value on these two vector fields. And what you can check is that a priori this definition depends maybe on the chart. So if I have like one chart in some neighborhood and like I choose a different chart, I might get like a different value on that side, right? Like a priori this depends on the chart because both of these vector fields depend on the chart. So if I choose a different chart, then I might end up like a different result on the right-hand side. But you can check that it's actually not the case, and that this right-hand side is independent of the charts, or like the whole definition is independent. So if you change alpha, then these ones change, but the right-hand side changes in the same way. Okay. But this formula is like relatively sometimes hard to work on with, because when it's kind of easy to work with is if you have these vector fields. If you can really calculate these vector fields and you have alpha really prescribed as a formula abstractly, then this formula is kind of okay to work with. But you really have to know these vector fields. Sometimes it's actually the opposite way. Is what you know is like how the one form alpha looks like in a chart, and you would like to calculate what d alpha is if you just know its chart representations. So let's derive a formula that says how to calculate that. Also a remark. So let's analyze this expression. Here we have Ts of the function. Let's say we take the derivative in x direction of that function for the function which is given by plugging in the vector field in the y direction. So that's this part here, this first part of the definition. We define alpha, the function f, by plugging in this vector field in alpha, get a function, and then take its derivative. So first of all, recall from last time that if you have such a function and we plug in this particular vector field which is given by the chart, then we always can write this one as the x derivative of f, but like f as like the chart representation of the function. F is the chart representation, which was defined as just composing f with the given chart. So that was like a formula that we established last time, that if you take the variation of f with respect to this vector field in x direction, then it's really just d of dx. But of course, you have to say, like now, for a function that is defined in x and y. So what we do is we just compose f with this chart to get a function that depends on x and y. And then we take the derivative in x direction. Okay. And so what we have to define now is the chart, or find is the chart representation of f, where f is this expression. But we have already seen that last time, that it's like the y component of the chart representation of alpha. So the chart representation of the function f, which is given as this one. It's the y component of the chart representation alpha. So this one was the this one is a one form 1D that we defined last time. So we can in particular write it, we call as alpha 1 dx plus alpha 2 dy. And it's exactly, the function f is exactly this guy. So this one is f, is the chart representation of f. So that's also something that we had last time, is that if you plug in y, you get like a function, and if you take the chart representation of that function, it's the same as first taking the chart representation of the one form, and then taking the y component of this. So it's in particular for what we now did is essentially calculating this expression in terms of the alpha phi. So let's say that it's a proposition to be solved, namely that if alpha 2 is the chart representation of alpha. So in particular, we can always write this one as alpha 1 dx plus alpha 2 dy. Then we get the following formula, that d alpha at a given point in x direction this expression is just given as d times dx. So that's the first time times the function f theta, which was alpha 2. And then we have to turn around to the same calculation, but like with x and y changed. And what we get is then it's d alpha 1, here alpha 1 and alpha 2 are just two functions defined on the open subset. So that's the formula that we get in the end. Is and here we have to say at which point of x and y such that this right-hand side is a function, and we have to evaluate it at the point, and the point is such that phi of x is the given point on the left-hand side. So we have two ways to evaluate. So that's the upshot is that we have two ways calculate d alpha. So the first one would be in terms of these vector fields. So that would be like say this formula here. Or in terms of these vector fields and alpha. So it would be this, or in terms of the vector fields where we just have dx and d phi, but then put the chart representation on the alpha, and that would be this formula right here. So depending on what kind of setting you have, it might be easier to use either the first one, if you, for some reason, already calculated these two vector fields, and you know alpha, then it's good to use that formula. But if for some reason you already have the chart representation of this guy, then you can just use this formula, and that's very simple, because you just have to take the x derivative and the y derivative. Essentially, what this also tells us is that we only need to consider the case where we have like something like a chart representation, right? So like something living on an open subset. So we can also just like look at that case in particular and like try to find like even nicer ways to calculate things. So on an open subset, we have just look at like an open subset, and we can of course think of that particular case as a special case of a chart, right? We have like one special chart which is just the identity. So alpha one form on D, and if you have that, just the identity here, then we find, using this proposition, that d alpha, and then we plug in our particular vector fields, which are just now, like, note over there in the formula it was with like the phi upstairs, but since phi is the identity, that simplifies to just get us dx and dy. So that's a function, and that function is just dx, and we have alpha 2 minus dy alpha 1 for alpha being just written as alpha 1 plus alpha 2 dy. So that's the result that we got from this proposition. So this formula. And the claim is that this formula actually has a nice expression in terms of alpha, namely claim is that d alpha equals to d alpha 1 wedge dx plus d alpha 2 wedge dy. So let's go through this formula and then see how we can derive it. So this means d alpha 1 is a function, which is alpha 1 and alpha 2 are just functions on an open subset. So alpha 1 is a function, so we take d of that function to get a 1 form. And then we have a 1 form, we wedge it together with dx, and what we get is in total a 2 form. And similarly, we do it here, but we just reverse the order. So here we have alpha 1 in dx, and here we have alpha 2 dy. So it's very, very simple to, you don't have to remember, here you always screw up with, do you first take the x derivative of alpha 2 or the y derivative of alpha 1, and you always screw up something. This one is just very simple, you can't, you don't have to think about that. So you just write alpha in terms of this one, and then the d is just taking the d over the function and making a matched product where there was a dot or the multiplication. And so it's really just taking that, making a d, and then putting a wedge in there, and then the same thing for the summons. So it's a very simple way to remember this formula. So let's see that this formula that we claim to be true is really the same thing as this. So